All right, this is a recording session for AS review. We are speed running through the AS syllabus in these review sessions. So I'm going to drop some basic ideas that you need to know for each chapter and suggested questions or examples that you may try. So chapter 9 is all about deformation of solid. Okay, so it's what I like to call the Young modulus chapter. Okay, so the first main idea that you need to know is that everything has a certain stiffness. Okay, so if let's say you have a material, maybe I'm holding this spoon here. So the spoon has a certain thickness, it has a certain stiffness, and when I apply force on it, it can deform, okay, and it can bend. So to describe that stiffness, right, we use this thing called a Young modulus. So Young modulus is constant for the same type of material. So for example, if you're talking about steel, whether it's a steel spoon or a steel fork or steel knife or a steel beam, they will have the same Young modulus. And Young modulus in your syllabus, sometimes or most of the time, they will use the symbol E, but they're not very consistent. Sometimes they will use Y. Don't ask me why, I don't know. I'm just telling you what A levels do. So Young modulus here is defined as the ratio of stress over strain, which means now we need to know what stress is and what strain is. So to stress someone out or to stress a material, apply some amount of force to that material. And you want to stress things out. So stress here is defined as a force per unit area. So let's say you have a wire. Okay, hang on, let me kill the notifications. Let's say you have a wire and your wire has you're going to apply force on the wire like so. So I'm going to copy the picture in notes. So this is your wire. And look, if you want to stretch the wire, you have to apply force on both ends, okay? It doesn't make sense if you only apply force on one end. There will be a force applied here, and then there will be a force applied here. If you apply force on one end, or if the force is not the same, this thing will not deform, it will just accelerate. Different chapter already, okay? So we apply equal force on both ends so that it will stretch or elongate, or I guess we could also compress. So there's no such thing as, oh, this force must be extension, compression. Okay, so to find stress, we will take this force, divide by the area. So the area would be the cross-sectional area that is 90 degrees to the force. Okay, this is A. So because it's force per unit area, it has the same unit as pressure. And the unit here is Pascal. Okay, so this is stress. And strain is defined as extension per unit original length. So extension over original length. So depending on what book or what you are comfortable with, you may put, I tend to put L over L naught. You can put X over L naught, whichever lah. Okay, so when we talk about strain, let's say I were to still use this example, this same wire, okay? So I'm going to stretch it a bit. And after stretching, the wire will be a bit longer than its original length, for example. So here is your extension, your L. You can put delta L if you are afraid that you will forget to minus the length difference, okay? And then L naught is the original length. So here to here is L naught. They are both lengths, so this one is no unit, unitless, okay? So if we bring it back into Young modulus is the ratio of stress to strain, but it can also be written as F over A and then divide by L times L naught. So you can put L over L naught. But if you are, sometimes I will write like this, F over A E for extension over L. It's the same idea, as long as you know what your symbols represent. Okay, so this is Young modulus. Whenever there is a ratio like this, there's obviously a graph, right? So we can have two types of graph. So I'm going to call this the second idea, where we talk about graphing. So there is the equation that you need to know, and from the equation, we can extend things out to your graphs. So let's think about your graph. The more common one is the Hooke's law graph, where we plot a graph of force against extension or extension against force. And you kind of know the shape of the graph. It would generally be a straight line until a certain point where weird things begin. No, not weird things, something like that will happen. Okay. So what is important to you at this juncture when it comes to this graph is actually to identify the important points, meaning you should know where the breaking point is, where the limit of proportionality is, and its respective definition. Okay, so these are all facts, and I won't delve too much into this because we need some time to do some questions, but I will provide the notes. So let me scroll a bit. You can find more comprehensive ones in the regular old notes that we have lah, in your OneNote. That is topical. I'm going to take some from your textbook. Okay, so a graph that you will get is something like this. Key points. So point A is what we call a limit of proportionality. Because after that, f is no longer proportional to x. So all points from O to A, here to here, f is still proportional to x. After point A, no more already. Okay? So to define limit of proportionality, you will say that the material, the extension of the material is still directly proportional to the force applied. Okay. What about point B? Point B is known as the elastic limit. So I think it's important to understand what is elastic deformation and what is a plastic deformation. So in a nutshell, right, elastic is when you are able to return to original length. So elastic means you can return to your original shape when we remove the force. Plastic is when there's permanent deformation. You stretch already, you let go of the force, your rubber doesn't go back to original length. It's like clothing. You buy this nice jeans and you wear it, and then after a while when you wash it, then it becomes looser and looser. Okay, no, that one, that's the elastic limit. Okay, so we can say that after point B is like, you can say after point B is if exceed B, the extension is no longer elastic. Okay, so if you want to define, if it's 2 marks, I will also mention what is elastic deformation. You can return to original length. Okay, C is normally where, so here to here, right, is no longer proportional, but still can return to original length. If B to C, you get plastic deformation already. Okay, and then here is basically nobody knows what's going on lah. Okay, so basically no need to point C lah. So you can say after B, so it can be B to C, plastic deformation happen. This is for ductile material. Not all material is ductile. Sometimes they are brittle, for example, for glass. So if the material is brittle, then the shape of your stress strain graph will be quite different. So if you just casually browse through your past year question, okay, questions that they can ask you regarding this graph are like this one from Feb March 18. Okay, these are all pretty like like this one. At which point does the graph stop obeying Hooke's law? So you see, where does it stop becoming a straight line? A. So this one is probably elastic limit. Okay, this one is probably called the breaking point. This is where it breaks lah. And then on top here, the highest point, we call this the ultimate tensile stress. So it's the largest amount of force you can apply before everything gg.com. See, you apply more force or the material begin to shrink back. The extension is, or rather the extension increase, but the force becomes less and less. Not shrink, sorry. So right now is a very weird situation where after you exceed this force, you don't need that much force anymore. The material will auto extend and then break. So if you ever plate and stretch anything like a metal or a piece of plastic, you will kind of know what we're talking about lah. Okay. So this is one of them regards to graph. The second one regards to graph is the area. Okay. So the force extension graph, the area under the curve shows you the energy required to stretch or to stretch the material. So this question is from Winter 19, paper 1-2. Here we have a rubber cord hanging from a rigid support. So basically, rigid support meaning the ceiling will not extend. Okay. Weight is attached to the lower end and it's gradually increased from 0 and gradually reduced to 0. So I add weight and then I measure the extension, and then I remove the weight and I measure the extension. And I plot and I get this graph. I notice that, let's say, for example, when I add weight from, let's say, 0 to 10 Newton, this is my extension. And then maybe I add to 20. This is my extension. So this is adding. I get this graph. That's what the arrow represents. And then I remove my weight. So if I remove my weight, right, I expect to get back the same length, but no. Let's say I remove to 10. Let's say I remove to 10, I get this new extension. So now, or even when I remove, right, for some weird reason, the length is actually longer. But never fear, for some reason, or the behavior of this rubber band, it can return to its original length one. Okay, so right now, what does the area represent? Okay, so when you think about this graph, what we have here is a graph that looks a bit like this. Okay, so when we stretch the graph, so I'm going to just casually rub off this part. The area under the FX graph, if you think about your chapter 6, is work done to stretch or elastic potential energy. So this entire area here, wherever this area is, this is the energy required to stretch your material. So here it can be called work done to stretch the rubber cord, which is coincidentally also equal to elastic potential energy stored in the rubber cord, right? Then when you contract, or when there's contraction, now, again, I'm just going to draw the graph separately for the first time. And after that, I'm not going to draw separately already. This is contraction. So think about when you release a rubber band. You drag and then you let go. The rubber band will have a certain speed. Either it hits you on your hand or it flies across the room. So that certain speed of the rubber band is actually the energy that you use when you stretch the rubber band, returning back being returned because energy cannot be destroyed. So whatever area under here is the energy released, the energy return. Normally is in the form of KE. When the band contracts or when we remove the load. Your muscle behave this way as well. Let's say you want to jump, you want to shoot a basketball, so you want to jump. You will drop your body down a bit to compress the muscle on your thighs and your glutes. And then you spring upwards. So your elastic potential energy stored in your muscle is converted to kinetic energy and GPE. So this one is KE and you can see there's obviously a difference, right? This difference here is because the band will get hot. Okay, so this difference in area here is the energy lost. Normally it will become heat because the layers of the rubber molecule will rub against each other. So what is the shaded area? The thermal energy dissipated in the rubber cord. Potential energy stored in the rubber cord is A. This is A. Potential energy stored in the rubber cord is this one. Work done by the rubber cord during contraction is this one. Work done on the rubber cord during contraction is also this one. Okay, so they could very well just shade a different area and ask you what it means. That's why I just did this graph law. Okay, so my suggestion when preparing for paper 1 is just to do as many past year sets as you can while learning from it. Okay, this is the force extension graph. A second graph, that's the more popular force extension, is the stress against strain graph. So this is the stress strain graph. Of course, if I go back to the force extension graph, the information that you can get is, I will list down here. Area is energy stored or removed depending on the direction of the arrow. And if we are still within Hooke's law zone, this gradient is equal to your spring constant K. Hooke's law, F is equal to Kx. K is a spring constant. Okay, so graphing. The graph that we can have, and again, the printout, I'll give it to you, don't worry. Okay, so the stress strain graph would be this one. It will have the same shape. It's just normally we will plot stress against strain now. But don't get too used to it. Sometimes just to annoy you, they will put strain against stress. Just to troll, because, things are getting pretty meh and they want to shake things up a bit, then okay. But don't worry, you can treat the stress strain graph very similar to how you would treat the force extension graph or the load extension graph, because it will roughly have the same shape. It's the same shape, something like this. Okay, so same shape and same consideration as fx. The only difference is obviously the gradient. Gradient, you will take ratio of stress over strain, so gradient here would be the Young modulus. And what about the area, miss? Well, if let's say it's within the Young modulus and you want to find area under the graph, okay, you will take half stress times strain. Okay, so let's say you just want to find this one now, just to make things a bit easier for us. So what is stress? Force over area. What is strain? Extension over original length. So this half Fx on top is actually the elastic potential energy. And AL naught, if you think about the dimensions of your wire, this is area, and here to here is L naught. So AL naught is volume. And half Fx is elastic PE. So my area is actually equal to strain energy. They call it strain energy because the material is being stretched per unit volume. So these are the only difference. So gradient is Young modulus for this. The area is this one. I think there was once the paper 2 asked you to prove lah, but otherwise everything feels relatively okay. All right. So that's it regarding the graph. Let's go and dig up some paper 2 question, or rather, let me go and see the winter 20 got come out or not. In the review session, I will focus on the winter 20 papers lah. And as usual, this kind of question may come out with kinematics because they don't have to be standalone. Okay, so we can try ON20. Nice and easy. I always say that when my students don't trust me. I think it's easy. It's easy. You gotta trust yourself. Okay, if you're wondering where to get the paper, I'm pretty sure you can find it online. It's not on paper.sc because the coder is not free to recode the subject. I mean, to recode the website. So you can find it on where you would normally find it. Or if you have access to my Google Drive, if you're my student, then you can find this drive. Okay. Or you ping me lah if you need access to it. Okay, so here, okay, let's look at, okay, hang on. I think I'll crop the whole question. Many words to read. So I think you should at least try the ON20 papers before you go for exam, just to get a feel and see whether you're ready or not. Are you ready? Who knows? Okay, let's go. Okay, define for a wire, stress and strain. Define for a student, stress and strain. I kid. Okay, stress is force per unit area. Or I guess you could say the ratio of force to area. Okay. Next, define strain. This will be extension per unit original length. So please make sure you mention the term original length. Okay, moving on. Can write equation for AS can. So you can write force divided by cross-sectional area, anything lah. You know what? I think this one I put cross-sectional area first in case they penalize me for this technicality. All right, done. A school experiment is performed on a metal wire to determine the Young modulus of the metal. A force is applied to one end of the wire, which is fixed at the other end. Okay, the variation of force and extension is shown. Okay, it's pretty normal to me. Maximum force applied to the wire is F1. Okay. The gradient of the graph in figure 4.1 is G. The wire has the initial length of L and a cross-sectional area of A. Determine an expression in terms of A, G, and L, the Young modulus E of the metal. Okay, I think I first want, so A and L are pretty normal stuff. I'm not that worried. I'm more worried about what G is. Okay, so to find G, I will take F1 divided by the extension. This is extension X, right? So let's say I call this E lah. So when the force is F1, the extension is E. So gradient G is equal to F1 over E. Okay, so I'm guessing that I'll probably need to use it later, but let me first write down what Young modulus is. Young modulus is the ratio of stress over strain. Okay, so stress as defined just now is F over A. Okay, I took a shortcut just now, but if you cannot, then you E over L. Okay, it's okay to take your time. So this E here will be F over A. And then this E over L you divide, so you multiply by L over E. And hey, I have F over E. F over E is G. L over A. Or in this case, they are using L. So I'll use big L. I'll use big L. Big L. Okay. So F over E is equal to the gradient, which is G. So E will be equal to GL over A. Okay. If you arrive at GL over A, you will get 1 mark, A1. Okay. And if you put stress over strain here, you will get your C1 already. So the rest is just substitution. Okay. All right, next. Student repeats the experiment in B1 using a different wire, twice the diameter. Okay, 2D. Twice the diameter of the first wire. The initial length is still L, remains unchanged, and the metal remains unchanged, so E is still constant. Draw a graph line representing, on figure 4.1, which is the previous graph just now, the new wire for the force increasing from 0 to F1. Okay, so if it's too much information, raw table. Because all of this is unknown, and sometimes people are not good with unknown. So wire 1, the length is L. Wire 2, the length is L. They have the same material, so you are Young modulus, you are Young modulus. We may or may not apply the same force, but we will apply the same force, so it doesn't matter. But the main thing that changes is area. So area is equal to pi d square over 4, right? So right now, the diameter is d and 2d. So 2d square means 4 times the area. So this area will be A and 4A. Okay, because if you need it, A is proportional to D square. So A over D will be equal to A2 over 2D. Don't forget this 2 got square. D square and D square left and right cancel. So bring up here, it will be 4A is equal to A2. It's okay to do an excursion at the side if you need it. So the area is 4 times. Now I'm going to go back to this thing and look at this. E, change color. E is equal to GL over A. This is constant. This is constant. So ratio is my best friend. G is proportional to A. So if A is 4 times, it means that the gradient will be 4 times. Is it 4 times? What do you think? Twice the diameter. Ding, ding. So you're going to get the same shape. But if you think about this, right? Miss, if it's gradient 4 times, I cannot plot for F1. Yeah, lor. So something is wrong somewhere. What is wrong? Where is wrong in the consideration? If you think about it. I need to drink some water. Hang on. Okay, so there are a few ways to think about this. If you are the type where you have a lot of intuition or you apply on intuition, you know a thicker wire will be less extension, correct? So if you just blindly follow equation, then you are a bit stuck already. Thicker wire, okay, I'm going to keep this here because this is like what is happening. Okay, let's write. Thicker wire is normally less extension because the wire is harder to pull. So if a thicker wire means lesser extension, then, or you could think about it this way, E is equal to F over A, E times L. Oh, this is L. Okay, don't think about the gradient, think about logic. First, your L is constant, E is constant. Okay, is the extension constant? Nope. We don't expect the extension to be the same. We are applying the same force. Correct? Because the force is F1. So all of this is constant. Meaning, right, I will have constant is equal to 1 over AE. Can? So I bring one thing up lah. I will get extension is proportional to 1 over A. Okay? So because of this, for the same force F1, let's say this is E, and then let's say this is E2. Then this will be A 2 over A1. Okay lah. I noticed that some students prefer to write a different ratio. I will write both. Never fear, I write both. So your ratio could look like this. E1 over A1 is equal to, inversely proportional. Then that would be E1 A1 is E2 A2. I mean, I personally don't like this, but if you want to, you can. I prefer the ratio of flipping. Okay, so when I say flip, I mean E1 over E2 is equal to inverse A2 over A1. Okay, and I can double check the unit, so whichever lah. It makes sense in your head, can already. Doesn't really matter. So E1 here is this value, this E. Okay, so we're looking for E2 in terms of E. So this will be E over E2. Your second area is 4 times the initial area. So the A and A can cut. That's how you got E2 as 1 over 4E. That means this E2 for the same force F1, the second extension is 1/4 the first extension. So while it may seem that you need to write a lot, the whole idea is thicker means less extension. And if you look at this one, you know that this 2 is inversely proportional. So it will be less by 4 because diameter is squared. So you can go through that process and think about like, okay, so now the extension is going to be 4 times less for the same force. So the same force, you have 4 times less the extension. How many boxes are these? 2, 4, 6, 8. 2, 4, 6, 8. Oh, this is 8, 16. So this is 16 boxes or 1.6, whatever lah, 16 boxes. This is E. So you want to divide by 4, there will be 4 boxes. 1, 2, 3, 4. So you're going to have to draw here. So when the force is F1, the extension is here. So same force, less extension. So right now, if you're thinking about, is the gradient 4 times? The answer is yes, the gradient is 4 times. So there are a few ways to look at it. You can do using the gradient way. Oh, this is also okay. It is not wrong. It's just sometimes students will get stuck. I need to 4 times the gradient, but I cannot draw. There's no space. Surely my answer is wrong. No lah, how you know? They purposely give you a lot of space underneath the line to mislead you. Don't be fooled. Okay, so this is the line. This is 2D. This is D. Gradient is 4 times. So yes, correct. So if here to here times 4, then the gradient also times 4. So it's 4 times steeper. Okay. If you want the gradient to be 4 times less steep, so 2, 4, 6, 8, 10, 2, 4, 6, 8, 20, 20 divided by 4, 5, 2, 4, 5, this one. So if we're talking about this, then this one would be if the diameter is halved, d over 2. In case this year they go and half the diameter instead of doubling the diameter lah. Thinner wire, easier to stretch, the spring constant is less. So in this case, this G, wait, my OneNote hang. I need to close some stuff. What should I close? I have nothing to close. Hang on. Oh, I complained about OneNote, then it calmed down. Okay, anyway. This one is when the diameter is half. So don't even want to say, oh, gradient is G over 4. This gradient is G, and this gradient is the best internet that we have, 4G. Okay? So I guess this is what I mean by you have to learn how to use ratio. Confirm will ratio something in this topic one without any values. Okay? Part 3. Another student repeats the original experiment, but he doesn't stop at F1. He increased the force some more until he get this curvy graph. On figure 4.2, shade an area that represents the work done to extend the wire when the force is increased from F1 to F2. So it's still area under the graph lah. So during the exam, you take out your pencil. So I'm going to pretend I have a pencil here. Okay, and you want to shade the area that represents the work done from F1 to F2. So this is the area. It must be between the Fx, the curve, and the x-axis. Okay, so you shade like that lah. Good enough there. If you feel insecure, then you shade the other side lor. The color looks different, so weird. Okay, I can highlight lah, but then you don't have highlighter during the exam. Okay, so one thing to note, whenever we look at work done or energy, is integration f dx. So it must be the area between the curve and the x-axis. So if you have any calculus brain or idea or background, you will understand, okay, that makes sense. We are looking for this area. If they flip the axis, okay, just let me find one where they flip the axis. In Z past year. Okay. If they flip the axis like this question in June 18, 13, to do it, but just in case the axis is like this, always check the axis. This one is extension against force. And then they say when the extension is 4 cm, so the area that we need to, crash. The area that we need to find is between the vertical axis and the curve or the straight line, whatever. It's this area. Okay, this is the area that we want. So it's always between the curve and the extension axis. Okay, so let me make it more. When I say x-axis, I mean extension axis. Okay, next. Explain how the student can check that the elastic limit was not exceeded when F2 is applied. So the elastic limit still may not, so proportionality limit already exceeded. But elastic limit is when the material can return to the original length. So how do we know the material can return to original length? We remove the load and then we measure the final extension. Okay. So what I'll say is I will remove the load gradually and measure the extension, final length of the. If the extension is 0, this means that the elastic limit is not exceeded. Okay, that's it. That's all you need to know. Hmm. Okay. Each student in class performed the experiment in B1. The teacher described the values of young modules calculated by the student as having high accuracy and low precision. Okay. What is accuracy? For many times, just to repeat so that we remember, accuracy here means close to true value. So maybe the teacher know the material that we use for the wire and all the young modulus that the students calculate are close to the true value. Low precision here means the sensitivity is too low. Okay, so if the sensitivity is too low, it means that maybe the true value example is 9.11 times 10 to the power 10. But some student will get 9, some student will get 8.9, some student will get 9.2. So this one is close enough, but they are quite far and they are very spread out. Some people get 8.7, but you average them, you get 9.1. So low precision here means that the values have a large range. Okay, because you cannot say it has a large sensitivity because sensitivity is related to instrument. So you can discuss sensitivity, which is the smallest scale reading, if it's a direct measurement. But we don't measure the young modulus directly, right? We find the gradient and we do some calculation. Okay, so this is not direct measurement. Values have a large range. This one is for calculation, experimental calculation, large range. Okay, that's it for this one. Let's look at another variant. Okay, the other variant also don't have a young modulus question. So I think this is pretty good. It's pretty comprehensive already. They test everything from energy to gradient to changing the dimensions. Okay. One less popular and normally only come out in objective idea for this topic is spring arrangement. So we can arrange spring in series or parallel. And how do we go about doing those questions? Okay, let me go hunting in the MCQ section for winter 20. Maybe we will encounter some interesting questions. Nope. Dun, dun, dun. The spring arrangement ones seems to be missing in your 1020. Good. Does it mean it will come out? Like I said, I'm not here to tell the future. I don't know. I wish I can tell the future, but I can't. Okay, so this means we need to go and dig out older past years. If you have any past year questions you feel that you want to discuss from this topic, you can feel free to do so. I'm just going to pick and choose some spring questions, like this one from June 12, paper 11. And you also have composite wire, which is actually two springs lah. You can treat wire as a spring, right? So this is a composite wire. Okay. This one is from June 13, paper 11. Okay, let's start from the top. We have some identical springs joined in 4 arrangement. I got no equation for you, okay? Just common sense. So, which arrangement has the same spring constant as a single spring? All right, so a single spring here is a situation where you hang a spring and then you hang the load. And the extension here is E. Okay? Let's say the load is W lah, all right? So right now you have to imagine you are spring number 1 or you are spring number 2. If you are spring number 1, you are supporting the load W, so your extension is E. Sure, spring number 1 is supporting W and spring 2, but I assume that the weight of the spring is negligible, okay? So it's supporting W. And then this 2 is supporting W as well. So it also has an extension E. So for the load W, the extension for A is 2E. Cannot be low. This load is still W, but you can see they are sharing the load. So this one will support W over 2. This one will support W over 2, meaning this extension will be E over 2 and this extension will be E over 2. So the total extension is E over 2. Very nice. What about this one? Well, this one, this whole side is supporting W over 2. But this spring, okay, this spring 1, spring 2, spring 3, spring 4. So spring 3 is supporting W over 2. Spring 4 also support W over 2 because they are taking half the load. 3 is supporting 4. 4 is supporting load. So if 3 have to support 4, we support the load, means that 3 also have to support the load lah. It's a little bit like if you sit on a horse, but you also carry a bag, the horse will have to take your weight and the bag's weight. 3 will have to take the weight of the spring, which is negligible, and also the load. But it doesn't bring that 4 doesn't take the load. They both take the load. Okay. So here is still W over 2. Here is W over 2. So if I total up the extension, I'm going to get E over 2, E over 2 on one side, and E over 2, E over 2 on the other side. So if I take just a single side here, the extension will be E over 2 plus E over 2, which is E. We want the extension E. The answer is C. But let's, for an exercise, find the extension for D in terms of E. This spring takes a load of W. So the extension is E. This two spring is W over 2, W over 2. They share side by side. So this will be E over 2 and this will be E over 2. So if I take the total extension, it will be E over 2 plus E, which is 3E over 2. So sometimes they can ask you arrange A, B, C, D in increasing extension, decreasing extension, whatever, you just follow lah. But right now they want a single spring, so single spring should have an extension E, that's why the answer is C. Okay, applying the same concept to this one. They're asking you which one has the largest extension, but right now the springs are identical and we change the load. Okay, so to make my brain easier, right, I'm going to assume that the extension is 1 Newton will create an extension of 1 cm. Can just to make my brain easier. Okay, so right now, I'll start with the 1A first lah. You support 2 Newton and the spring. You support 2 Newton. So your extension top spring is 2 cm. Your extension also 2 cm. So your total extension is 4 cm. Okay? 1 Newton, 1 cm. 2 Newton, 2 cm. So total is 4. 1 Newton. So we are all arranged in series or one on top of the other. So everybody is also supporting 1 Newton. Meaning you get 1 cm here, 1 cm here, 1 cm here. So this is 3 cm. So B lost liao. What about C? C is 6 Newton, but 6 Newton is shared equally because this is what we call spring in parallel. So you get 3 Newton, you get 3 Newton. Meaning your extension here would be 3 cm. This will be 3 cm. So the extension here is 3 cm lah. Nothing much to do about this. This 8 Newton is a bit of a pain because this is 8 over 3 Newton. 8 over 3 Newton, 8 over 3 Newton. We share the load. But the good news is the extension is also 8 over 3 cm. So if it's 8 over 3 cm, I'll press my calculator to find 8 over 3. I don't know where's my calculator. I had it yesterday, but hang on. Let me press my phone. 8 divided by 3. 2.66. Okay. 66667. So you can see the largest extension is this one. The least extension is D. Okay. So if you think about how the spring arrangement will affect how the load is being shared, this kind of question is pretty easy. All right. Now what happens when you have a composite bar? For example, now we have copper wire and then steel wire and then support a weight. Okay. So here is said that the Young modulus of steel is twice the Young modulus of copper. Cu for copper. 50 cm length copper wire. So I'm just going to call this L copper. Diameter of copper wire is joined with a 50 cm length of steel. And the diameter of steel, making a combination wire length of 1 meter. Okay. Combination wire is stretched by a weight added to its end. Both copper and steel wire will obey Hooke's law. What is the ratio of extension of steel to extension of copper wire? So for this one, you think about Young modulus law. Young modulus is F over A, E over L. Okay. I can see that the length is constant because the length is both 50 cm, 50 cm copper, 50 cm steel. So this length is constant. The force is also constant. How do I know force is constant? It's like the spring one. If I pull down by 2 Newton, you have to support 2 Newton, you also have to support 2 Newton. So whatever force I put here is still going to be the same force. So F is also constant. And they are not the same Young modulus, so Young modulus is not constant, and A over E is not constant. Okay. So right now, I have Young modulus is inversely proportional to 1 over E. I guess I can rearrange. I can say extension is proportional to 1 over Young modulus times area. So I want the extension of steel over the extension of copper. Okay, I would take the Young modulus of copper, flip it because it's inversely proportional, divide by the Young modulus of steel, multiply by the area of copper, yeah, multiply by the area of steel. Flip it. So Young modulus of copper ratio steel. Copper over steel is half, right? Because steel is twice, ma. Steel is twice of copper. Okay. Diameter, leh? Diameter of copper is 2 mm. Sure. The diameter of steel, wait, 2 is here. The diameter of steel is 1 mm. But then don't forget square, lor. Because diameter square, ma. Area is pi d square over 4. The pi will cancel off in ratio. So here I'll have 1 over 2 times 2 over 1 square. The answer is 2.0. Okay, so this kind of ratio is pretty common, whether it's objective or structure. Just understand that when you have a composite bar, you arrange like this, they both share the weight. Okay, but not always your composite bar is arranged this way such that they both share the weight, right? In this question that I found from ON20 21. Paper 21? Paper 23? Wait, let me check. ON20, paper 13, sorry. ON20, paper 13. Here, you see steel wires, 4 of them, 1 go. So in this case, they are sharing the 20 kg load. You take 20 kg, sorry, you take 50 kg, sharing the 200 kg load. Everybody take 50 kg each. The wire obeys Hooke's law. Okay, how far would the platform descend because of the extension of the wire? So they are looking for E lah. Okay, I mean we have L, we have D, and we have the Young modulus E. Substitute only. Young modulus is F over A E L. Okay, so I want to find extension. I'm just going to rearrange a bit lah. So the pressing will be less pain. So force here is 50 kg for each wire. So this is times 10, 50 times 9.81. So remember to convert to mg law because it's force what? The original length is 5. Area, pi d square. I guess I can just change to 1.5 lah, huh? Times 10 to the power -3 square. This is area. Okay. And the Young modulus, this is E, my bad. 2.1 times 10 to the power of 11 Pascal. Okay, time to press calculator. 9.81 times 5 divided by pi. Hey, I got 1.65 times 10 to the power -3 meter. So this one, okay? Very easy one, Young modulus, if you know what you're doing. Okay, and this one, if you want to find work done, just to finish up the question, your force is this, your extension is this. What is the work done? Work done is half Fx lah. Okay, so you can just take the force times mega times 10 to the power 6. Extension is -3. 5 mm, 0.5 times 7e6 times 5e-3. We get 17500 joule. So C. This is okay. Let me see if there are any paper 2 questions that I wish to highlight from the past years that you should go and try. Okay, so there was a year, I mean, the collection that I have stops at 2019. So I don't have 2019 questions. Let's see, is there anything interesting? I mean, I don't know. That means you can go and try lah. It doesn't matter. Okay lah. In the interest of finishing on time. A lot of times, the Young Modulus question will be combined with either equilibrium, chapter 5, or kinematics, or projectile, or forces, because we can kill a few chapters in one question. Because paper 2, we can only ask maximum 7 questions. So it's more worth it if I combine, for example, like this one, the ratio of stress and strain calculation to an equilibrium question. I can test both law. Do you know equilibrium? And some more they test you SI based quantity. Very nice. Okay. And like for example, this one, there's work done. This thing is going to drag the joker. And then you want to find the pressure of the ski lah, the diameter of the wire lah. You're given Fx and then change in strain energy. So it's very common to see a kinematics question in combination with a Young Modulus question. A pure Young Modulus question like this is hard to find. But this question is actually quite interesting because you are given a very strange looking Fx graph. It's still an Fx graph, but it's F against L. So I think I will end with this question from May, June 18, paper 2-3. Although I'm pretty sure I've discussed it in class, but why not? There are 2 questions like this. The very weird one. This is another one. May, June 7. I mean, winter 17, paper 2-3. In fact, they're almost identical in execution. It's like they never change anything. Or I didn't change the question. Who knows? Okay, so this one, the second one is this. Okay, maybe I didn't change the question now, but they're all about the same. Okay, sometimes you get some weird graph like this. No problem. NBD. Okay, and also just want to briefly mention that this is how they apply the force F1 lah. This is the experiment setup. Put it through a pulley. There's a scale here. When the marker on the wire move, we can measure the extension. That's how they got the graph of Fx. Okay, the rest is pretty standard. There are not many questions. All like that one. Okay lah, so I will do the slightly anomalous looking graph, which is, I think, from May, June 18, paper 2-3. Hopefully my compilation is correct. But let me check. And that will be the last question for chapter 9. It's a short topic, so we generally don't expect many questions. Yes, this is May, June 18, paper 2-3. So we start off by asking you to, as usual, define Young Modulus, ratio of stress over strain. So I'll just leave that to you. And you are given a pretty slightly strange looking, but not too strange looking Fx graph. Okay, you're asked to determine the spring constant and the strain energy stored in the rod for 90 kilonewton. Okay, so to do this, to find the spring constant, you're obviously going to use the some form of the relationship F is equal to Kx, right? So you need to use the gradient. For AS, generally, they do allow you to do value substitution, okay? Or they allow you to use a point. Never mind. Let's see. We'll start with F is equal to Kx, okay? And if you want to find K, you will take, but you see, you look at this graph, it is the original length against, the final length against K. All right. So you could take a point and substitute. I think they allow. Let me double check. Okay. Nope, they allow. So fine, it's fine. It doesn't matter whether you use the gradient or you use gradient, because gradient is generally more legit. So you got F is equal to Kx, but this graph is L against F. But this L is equal to, so you want to find extension X, you will take L minus L naught, right? So this L will be equal to L naught plus extension. So this graph, L is equal to, let's say gradient GF, the equation of this graph. Your L is actually L naught plus X, and this is equal to GF. So I rearrange. If let's say I want to find the relationship, right? Okay, this one feels a bit redundant. Let me check the marks. Is this very little mark for much work? If little mark, much work, I'll just substitute. Too many PDF are open. Yeah, 2 mark only. Okay lah. No need to linearize. My bad. Just finish A2. My brain is like, should we linearize because it's A2? No, you're teaching AS. Okay, fine. So you're gonna substitute law. Find a value. Don't go and take 0 because you have no force. So maybe I'll take 90, okay? This is 90, 148 mm. When the force is 0, this is your original length, L naught. This is 150, meaning your change length is 2 mm because you change from 150 to 148. Okay, so you can write a sentence lah. When the compressive force is 90 kilonewton, okay, the extension is equal to 150 minus 148, which will be equal to 2 mm. Then you can substitute all. F is equal to Kx. 90 times 10 to the power of 3 is equal to K. 2 mm, 2 times 10 to the power of negative 3. Okay, so you can rearrange, you can find your X. Sorry, you can find your K. So I have my calculator. 90 E3 divided by 2E negative 3. So this will be 4.5 times 10 to the power of 246. 10 to the power of 7 Newton per meter. Determine the strain energy stored in the rod for 90 kilonewton. So the whole thing lah. If you want to find the strain energy, the most straightforward way is to use half Fx. Because you already have alpha 3. Your extension is 2. So 90 joule. Miss, do we find area? You can find area lah, but then the area is this area. If you're looking for area, it is this area, which is the same what half f, which is 90, times x, which is the base of the triangle. So the area is the same. Okay. Oh, no problem. Next. The rod in B has a cross-sectional area A made of metal Young modulus E. It is now replaced by a new rod. Yeah, so familiar one. So familiar, right? Same original length. The new rod has a cross-sectional area of A over 3 instead of D over 2. And it's made out of Young modulus 2E. The compression of the new rod still obey Hooke's law. Sketch how F and L will change from 0 to 90 kilonewton. Ooh. Okay, I'm still going to take 90 kilonewton as my reference point. So if I list down all my quantities, I'm going to go with the initial wire. I have 1 and 2 lah. Initial and final wire. And also, Young modulus is F over A, E times L. What is constant? L is constant. Let me check mark. L is constant. I'm still taking 90 kilonewton, so F is constant. The Young modulus is double, so it's not constant. Area is not constant. I want to find the extension. Okay. So I'll take E1 over E2. Okay, bring up over here. Is equal to A2 over A1 times Young modulus over this one. Because from here, I will get E is proportional to 1 over AE. Okay, initial extension is 2 mm. I don't know what the second extension is. Okay, again, this is for 90 kilonewton. Okay, and this area, the second area is A over 3. The initial area is A times. The new Young modulus is 2E. The initial Young modulus is E. So you can list down in the table format, or if you are feeling a bit lazy like me right now, you can do this. That's not a problem. You get 2 over 3 is 2 mm over E2. Wow, wow. Cross multiply lah. E2 is 3 mm. So this second extension or change in length, or actually it's not extension, it's actually being compressed, is 3 mm. For 90 kilonewton, for this second wire, E2 is 3 mm. Okay, let's go back to the graph. 90 kilonewton, 3 mm. 3 mm meaning I will drop from 150 to 147. This is E2, 3 mm. This is E1, 2 mm. Okay, lor, then draw a straight line. Oh. Let's draw a straight line. Somewhere here, like this. Okay, not like this. I make sure you start from the same original length, so it should also intersect with 150. Okay, that's all. This one is the line in 4C. If your straight line is below the original line, you get 1 mark. If it passes through this coordinate, you get the second mark. I cropped the mark scheme for you. So if they ask in combination with other kinematics question, the question should be relatively straightforward. You're either asked to find the ratio of stress or the ratio of strain. If they ask it on its own like that, you may be asked to redraw a graph. Or like the ON20 paper 2-1 question, you will be asked to draw a graph with no arbitrary values. You are still going to employ the same format where we find what the new extension is. In this case, it's even nicer. The Young modulus is the same because it's the same material. All right. So what did we learn, or what do you need to know in this chapter is those few information. The basic definition of what Young modulus stress and strain is for calculation purposes, how to interpret various graph and the important points, whether it's force against extension or stress against strain. I didn't really cover much on this because you will need to treat the graph according to the graph that you get. Two more objective questions regarding this. And then sometimes they will change the material or the dimensions of the wire and you are asked to plot a new graph. Also, the area under the graph is energy, so don't forget that. And also, sometimes they ask about spring. So if you understand the idea of if you arrange like this, you are taking on the person's load and the person still have to carry their load. If you arrange side by side, they are sharing the load. Then whether it's like this, no share, or like this, all share, is the same thing, whether it's wire or spring. And I've done another one just to show you how different how question can be like. You need to do more past years. Okay, and that's it for chapter 9.